So we were talking about off policy uh, evaluation or estimation. And even though I have not worked on this topic much, I have read a few papers, and whatever I'm going to talk about is on the basis of my understanding of those papers. I think it's an important topic, especially in today's world, especially, and if you are going to any of these big companies, then you would probably need a lot of background knowledge in off policy estimation. And so the idea is, as we discussed in the previous class, the data was collected uh, with policy mu b, called the base policy or behavioral policy or uh, data collection policy. So there are three different names depending on which paper you are reading, and you want to estimate q pi or v pi. Sorry, v pi e. Oh no, I'm using pi. No, mu. Okay, so to give you an example, suppose you are. So let me give you a bunch of. We did talk about its connection to high energy physics in the previous class, towards the end of previous class. So I'm going to build upon what we had discussed in the previous class. But there are many reasons why you would want to do this, and very different areas where this particular problem has appeared again and again. So we did talk about high energy physics, where you wanted to figure out when a particle is going to become some other particle, and you wanted to do the simulation, and you wanted to speed up the simulation, and you used what is known as importance sampling to do that, and we'll talk about importance sampling today. But later on in economics or in business, people want to understand, what if I had done something else? So there's a counterfactual situation, and they want to estimate what would have happened if I had done something else. So, for instance, the government might say that, look, I want to establish a policy, and I want to figure out what's going to happen if we instead, like we have two or three different policies. I have the data collected with respect to the current policy. I have a new policy, and I want to figure out what's going to happen under the new policy. How much business is going to grow? How much, uh, or whatever. How many poor people are going to come out of poverty and things like that. So whatever the new policy is, that's mu e, and I want to estimate the value of mu e based on the data that I've collected for mu b. So in economics, this is studied under the umbrella of what is known as uh, causal inference. Okay, so causal inference also has very similar vibe, and a bunch of people in economics have also won Nobel Prize for studying problems of this type. So it's an important problem, okay, from economics perspective, from reinforcement learning perspective, uh, and from high energy physics perspective. Okay, in reinforcement learning, we did talk about the Tesla example. So people are driving cars, so they have some policy mu b, and you want to figure out what the Tesla policy should be. And in order to that, if you come up with a policy, how do you evaluate whether that policy is a good policy or a bad policy when you have data logged from some other policy? So that's one example. The other example is in a platform setting, you are coming up with recommendations for people. So you are responsible for recommendations at Amazon. You have collected data from the previous recommendation policy. You have come up with a new recommendation policy. You think that's the best recommendation policy. So the previous recommendation policy was using, I don't know, matrix factorization method. You have used graph neural network to come up with a new recommendation policy, and you want to figure out how much Amazon is going to gain using the graph recommendation algorithm. Okay, so roughly, those are the different areas where this kind of tool is very important. And by the way, in Amazon, companies like Amazon, if you're not able to estimate this, that policy will never get implemented. Okay, so you have to show in some sense that whatever policy you have come up with, using whatever technology you feel is important, you have to show that your policy is going to do well. Otherwise, they are not going to implement it on actual system. And if it doesn't get implemented on actual system, you don't get your promotion. If you don't get your promotion, you get out of Amazon. Okay, so and Amazon just laid off 18,000 people. Nothing to do with this, but that kind of thing happens in life. So it's an important topic, and that's why I'm covering it. So there are three different scenarios that I'll be considering in today's class. So scenario one is my time t is equal to 1. Second is t equals to finite. And then the third one is t equals to infinity. So whenever I'm talking about the value function or the Q function, most likely we are going to talk about value function. You could have only one decision step, one time step. You make a decision and the entire simulation stops at that point of time. You could have a situation where you have finite number of time steps. You have to evaluate the policy over a finite number of time steps. And then the third situation is you have an infinitely long horizon with discounted cost or discounted reward, and how do you evaluate V mu E in those situations. So t equals to 1 is studied in economics under the umbrella of potential outcomes theory. This one is studied under the umbrella of importance sampling. And this one is studied under the umbrella of fitted Q iteration, I think. Fitted Q iteration. Or min-max Q iteration, min-max. Min-max Q learning. Okay, so that's what we are talking about. So as I mentioned, for potential outcomes, people have received Nobel Prize for working on potential outcomes theory. Nobody got a Nobel Prize for importance sampling, but it's an important tool that was developed in nuclear physics and then percolated into reinforcement learning. And this is very much reinforcement learning focused tool. So let's talk about the potential outcomes theory. What is the idea? So my idea is I have a state S, I take an action A, I get a reward R, and this is given as the probability distribution. So I'm in t equals to 1 domain, is PS. Oh, I'm using, yes, I'll use IU to be consistent. IUR. I'll use rho of I, that's the initial state, mu of U given I, and then some probability R given I comma U. This, of course, could be mu B or mu E. So you have data I K, U K, R K. K equals 1 to, let's say, capital N. This is IID, IIDP. Let me use P mu. P mu and P mu B. So I've collected data of the state, action, reward according to mu B. policy, and these are all IID data sets. So to give you a concrete example, let's say I'm running a Facebook marketplace. I look at your post history. So you are the person, you are the nth person. I look at your post history and I saw that you are posting a lot of dog pictures. So I assign to you advertisement on dogs, whatever, dog food. Okay. And then I saw whether you bought the food or you didn't buy the food. If you clicked on the ad, Facebook got some money. That's the reward R that Facebook is getting. And so you have n such people, you have population of n people under the recommendation policy mu b, where people saw dog pictures and half of the people saw dog food and the other half of the people saw dog posters. Okay, because they don't know, as an advertiser, I don't know if you're posting dog pictures, is it because you love dog, you hate dogs, I don't know. And so I'm just going to just, according to some policy mu b, I'm going to just throw random advertisements at you, and I'm going to collect all this data set. By the way, Facebook and Microsoft and all kinds of companies do that. That's really an important business problem, and they make billions of dollars doing that all the time. So you've collected this data, and as I said, you came up with some new policy, mu e. Okay, I'll give you another example besides Facebook. So this is an example from India, and I'm sure there will be equivalents everywhere else. So in some state, the government said, look, I'm going to look at people who are below the poverty line. So the poverty line across the world is defined as $2 per day or something, like the income is $2 per day or something. So if you are below $2 per day, I'm going to give you X number of dollars in your account. And I'm going to see whether the poverty level after a year went up or went down. Okay, so this is a Nobel Prize winning kind of idea. So now you look around the world, wherever this kind of experiments have been done in the past, and you collect this data set from different parts of the world or different parts of the country or different villages in the country. And you have the data, and now you are figuring out whether this policy of putting X dollars in somebody's account or Y dollars in somebody's account, should it be rolled out across the nation or not? Okay, and that's mu e. And so economists study, so the potential outcomes theory tends to study problems of this type, whereas in Facebook you are studying problems of somewhat different type, but the math is the same. Okay, so what's the assumption? Weak positivity. So these are assumptions from the economics literature, so it may not correspond to the corresponding terminologies that are used in statistics or probability or electrical engineering or whatever. So support of mu e given I is subset of the support of mu b given I. Second assumption is consistency. R reward depends only on A, only on you. I'm sure you will find papers which are talking about reward that depends on both U and S, U and I. But for the time being, just assume that the reward is purely a function of U. And unconfoundedness the probability of reward given reward comma action given u given I is probability of r given I no the reward, let me write reward as a function of u and u prime is a function of reward at u given I and probability of u prime given I. So the reward at u and u prime, which is some other actions, are independent, conditionally independent given the state. So remember, reward is a random function of u. I guess I should say reward only depends, reward ru depends on u but not u prime. So reward is a random variable which depends only on u, but it doesn't depend on other actions that are possible, because reward is a random variable. Okay. This condition, consistency condition, generally doesn't hold in social networks. So the idea is, suppose I show you an advertisement, then the reward that I get by showing you an advertisement only depends on me showing you the advertisement, but not me showing the advertisement to your friend, and then your friend happens to talk to you off the platform. So those are the kind of conditions you want to preclude from by making this consistency assumption.
Being specific about the action.
Yeah. So essentially, the idea is, because reward is a random function of u, you could have a situation where other potential actions that you have taken would influence the reward, because you are, let's say you are running an experiment on Facebook level, and you know that friends talk, and so if you saw a dog poster and you happen to buy it, and then your friend sees it, then he or she is also going to go and buy the dog poster from Facebook, and then Facebook is going to think, oh, he or she bought the poster because I showed him the advertisement, but actually the advertisement didn't really result in the buying of the poster. It was because you saw the poster at your friend's place, right? So that's the kind of problem that happens when things are inconsistent. But I guess that's the technical assumptions people tend to make. Same thing happens in economics situation also, like when I said that, people are getting some money in their account, and then the economic growth happens for that particular family. But of course, if everyone in the village is getting a lot of money in their account, then the growth is going to be much larger, because now people can start trading a lot more goods and services among each other. So it's a very strong assumption. It doesn't hold in practice in many settings, but anyways, that's the assumption for the math to work. And that's the assumption that gets you Nobel Prize. Okay. So the question is, I want to come up with the expected value of the reward if u is picked according to mu e. So what's the expected? So now remember, this is the one from which I've collected the data. And now I'm trying to figure out what's the expected reward if I instead use some other policy to do this, to estimate what the reward is going to be. And so the simplest idea is, this is how about I write it as, this is the expected value of reward multiplied by mu e a given u given I over mu b u given I, and this u is generated according to mu b. Right, so you divide it by mu b, and then you multiply it by mu E, and this is equal to, well, right? So do all of you agree that that there is an equality here? So if you take the integral of the expected reward, this mu B and this mu B will get cancelled, and what you will get is a expectation with respect to mu E. And so that's roughly what the potential outcomes theory is suggesting. Okay, so does that make sense? This is the main result of potential outcomes theory. If you, and then you can, so now you want to compute this expectation, so you can do the empirical mean, right? So all of you know how to do empirical mean. You've done it multiple times in assignments. So you can do the empirical mean, and you can try to estimate what the expected reward is going to be under the new policy. Now here are some issues. In the Tesla example that we talked about, you know what the updated policy is going to be because you are the person who has built that policy on your computer. What about the behavioral policy under which the data was collected? Right? You don't have that policy because there are millions of drivers who are driving on the road, and you're essentially collecting that data set. So then what do? Well, you end up estimating mu B and you replace it with mu hat B. So in practice, you have expected value of reward mu E over mu hat B. So because what you have to do is, based on the states and actions that you have seen, you estimate mu B. Remember, you have that data set right here, and then you take the mu hat B in the denominator. Yes.
So in the Tesla,
Yes.
right, you have to
It is their policy. It may or may not be optimal.
their policy,
Right.
right? But if both of them were separate and the policy would know that, or would know, right?
So it depends whether you know mu B or not. So in the Amazon example, it was your recommendation policy before and it's your recommendation policy after. So you know both mu E and mu B. In Tesla case, because you are logging data from other people's machine, you don't quite know what their policy is. So you tend to estimate that policy and then use that in this expectation. The other issue that appears is this first condition, right? So, you know, what is support? Support is at what actions the probability was positive, okay? Now, the problem is sometimes a positive number could be 10 raised to minus 10, okay? So if mu hat B is 10 raised to minus 10, you multiply it by mu E, which is 10 raised to minus 2, and you have 10 raised to minus 8 here. 10 raised to 8 here, that gets multiplied to the reward. And that creates a problem. Okay, so then what do? Well, you have expected value of R mu E max epsilon mu hat B. Okay, so these are all the different hacks that people have used. You pick an epsilon and then you do max of mu hat B and epsilon to solve this problem. So the variance of this particular method could be extremely high, and that's because you could have situations where mu B is very small on certain actions, but mu E turned out to be very large on those actions. So there is a huge disconnect between the new policy mu E that you want to estimate and the behavioral policy or base policy from which you have actually done the data logging.
Normalization cannot help.
Yeah, so normalization is another way by which you solve this problem. So you divide it by expected value of mu E over mu hat B. What I don't know is whether this one is a consistent estimate or not. So that's the part I don't quite know, and I haven't read enough to know whether would this be equal to this or not. Okay, or what's the difference? What's the relationship between this and this? But this is also something that some people have tried in the past. I've seen it in the papers. Any other question? Okay. There's another estimator called doubly robust estimator, which is different from this. And what's doubly robust estimator? You have expected value. Okay. You have Q of I comma U equals to expected value of R given IU. You use a neural network and you train this based on this data set. You pick IK, UK, and RK is the output, and then you train a neural network. You get this function Q of IU, and then you have the estimator is expected value of mu E over mu B, U given I, U given I, R minus, let me call it Q hat IU plus Q hat IU times summation. U is summation over U, Q hat IU, mu E, U given I. So this is known as a doubly robust estimator, which has a lot of papers in 2010 to 2020. The doubly robust estimator was the rage of the research world in the last decade. Okay, so a lot of you will find a lot of very good papers in statistics and in economics that are talking about doubly robust estimators and the survey and all of those things in the previous decade. So these are all the different techniques that have been done for t equals to 1 case, where you have only one time step and you want to figure out if your algorithm is, the new algorithm, new policy is better than the old policy or not. And how do you define the better? You want to compute the value function under the new policy. Okay, any questions so far on this? The biggest drawback of all of these methods, I mean, not the biggest drawback, but certainly many of these methods are high variance methods because of this ratio. You need to know both mu E and mu B in this particular case. If you don't know mu B, you replace it with an estimate, and then you take the ratio, and then you hopefully get a reasonable solution. The best case scenario is if you have, so remember you were doing epsilon greedy policies at some point of time. So you're putting your weights on all different actions with probability epsilon over n. So if you pick your mu B where you have epsilon over n, so you pick your base policy in a way that you have some positive probability given to all different actions, then you might do much better in terms of the estimation. Okay, you won't be able to do it in every case. So for instance, if you are in Amazon and you say, oh look, we'll use this cool algorithm that I've developed for 90% of the population, and rest 10% of the population will be exposed to this epsilon over n type of recommendation, the manager is going to shut you down immediately because that's going to cost Amazon $1 billion over a year. Okay, and nobody wants to lose $1 billion because you wanted to run some experiments. Yeah.
Should the sigma, the second term, the sigma term,
Yeah.
be inside the expectation or outside?
It is inside the expectation because you are taking the expectation with respect to u, and then I still remains the random variable because I is distributed according to rho. So this expectation is with respect to I here, and this expectation is with respect to I and U for this particular term. Okay. Any other question? You can think of this term as an inner expectation of Q hat IU, where U is distributed according to mu E. So that's inner expectation. This is still a function of I, and then you are taking an outer expectation with respect to I. Any other question? Okay, so what you should be clear, I mean, I'm assuming that all of you are clear that once you have this expectation figured out, how do you compute this expectation using data? So you use the usual averaging technique to figure out what this expectation would be equal to, or come up with an estimate of this expectation using that data. Any further questions? No? Let's look at the finite T, the importance sampling method. Can I erase this board? Okay. By the way, this theory is extremely rich because right now we talked about the IID data collection, but there are, of course, papers written on when you have a long sample from a single stream. So how do you deal with those kind of data? But we are not going to talk about it because, again, I just want to have one class on off policy estimation, not multiple classes. So we'll try to finish it today itself. Doubly robust estimator is better than this particular estimator because it has lower variance in comparison to this in some settings. Okay, let's talk about the importance sampling at the finite time step. So all of you remember importance sampling from the previous class. So you have the original Markov chain, you want to simulate it, but you don't have you think it's going to take a lot of time, so you come up with some new Markov chain and you evaluate the function over a new Markov chain, and then you multiply it by some ratio. So let me write it down again from the previous class, and let me know if I'm using the wrong notation. So I wanted to compute the expectation of f of x naught to xn. Was it xn or xt? Let me use capital T because that's my horizon. And this is under the transition kernel P of xt given xt minus 1. And this is the same as summation x naught to xt f p of product t equals 0 to t minus 1 p of xt plus 1 given xt, and then rho of x0, which is the same as summation x naught to xt f product t equals 0 to t minus 1 p xt plus 1. This is something that I had written in the previous class, so you don't need to write it down, but I just want to keep it on the blackboard. What was this measure that I picked in the previous class? What was in the denominator? Can someone check and tell me? Was it new or was it? So New? Okay, perfect. And I'm going to call this variable LT. So some people use W, some people use L, depending on the paper you are reading. And this stuff that I'm going to talk about comes from the paper by Peter Glynn. The title of the paper is Important Sampling for Markov Chain Asymptotics for the Variance. And this paper was written in 1991 or 1990 or something like that. And as I mentioned, it was used in nuclear physics, but nowadays people are using it to track objects in the space, debris in the space. So there was a talk in ISE department a few days back on discrete event simulation. So discrete event simulation tends to use importance sampling technique. Okay, so this is K is the new Markov chain that I have created. This was the old Markov chain which I needed to compute, but this one takes a lot of time, so I'm going to divide it by new Markov chain K, which I have handpicked. I have hand designed this particular Markov chain, and I'm going to use this ratio. I'm going to call it LT, and then I'm going to do the simulation with respect to this new Markov chain K and this new initial distribution nu. So in our case, in the case of reinforcement learning, xt equals to it comma ut, and p of it plus 1 ut plus 1 given it ut is given by p it plus 1 ut multiplied by the policy mu e ut plus 1 given it plus 1. Oh, sorry, the P will be mu B. This is the base policy. And then K will be P times mu E. Oh, no, sorry. I think I was right earlier. This would be mu E and this would be mu B. So P is what we want to simulate, but K is what we have data for. So K is what we have data for, and P is what we want to simulate. Okay, any questions so far on this? Okay, so so I have a finite horizon time window. I have some cost function or some reward function f, which is a function of the entire trajectory. So in our case, this f is going to be, okay, I need to write f also. So in our case, f of x naught to xt is summation alpha raised to t r of itut t goes from 0 to capital T. Okay, I think I have pretty much mapped everything. And in our case, in most situations, nu will be equal to rho. So the initial condition, initial distribution is not going to change. You can definitely change it, but generally speaking, in reinforcement learning, people don't change the initial distribution. Okay, so in the nuclear physics, people are interested in general functions of this type. In reinforcement learning, people are interested in specific functions of this type. So as a result of which, if you plug in this particular thing here and you take the appropriate summation and so on, the entire expression is going to simplify quite a bit, and the updated expression. Okay, one thing that maybe I want to talk about. What do you think is this? So remember, rho is equal to nu, so this term is equal to 1. What does this probability looks like? What does this LT looks like? Can someone tell me? So observe this P and K from here and go back to this expression, substitute it. What do you see? What is LT equals to?
Over UV product.
Sorry, product of
Over O
mu E
over
U T plus 1 given IT plus 1 over mu B UT plus 1 IT plus 1. Maybe T goes from, no, T, well, let me write it as this. Mu E UT given IT over mu B UT given IT. So this is what this LT is going to be, and I'm going to define L sub T as the same product. LK T equals 0 to K of the same thing, mu E over mu B. Okay, so there are three different estimators that people have studied in the past. One is known as crude importance sampling estimator, which is V hat pi e, sorry, mu E equals to LT times summation T equals 0 to capital T alpha raised to T RT. And if you have multiple samples, if you have multiple trajectories, you just take the empirical expectation with respect to each of those trajectories. So RT is your observed reward, alpha raised to T is your discount factor raised to T, and LT is this particular product. This is the crude importance sampling. Then there is per decision importance sampling, which is V hat mu E equals to summation T equals 0 to capital T alpha raised to T RT times LT. And the third one is called MIS. What does MIS stand for? I haven't written it down. So anyways, the third estimator is somewhat interesting. So I have already used L, K, I, J. J is not used. No, J is next state. M is not used so far, right? Okay, so I'll use M. So what is MT? MT is defined as P probability of IT. So MT is, let me write it as IT UT given I0 distributed according to rho, and UK is distributed according to mu E given IK over probability ITUT mu B IK. And the third estimator, MIS, I'm forgetting what this M stands for, but here V hat mu E is summation alpha raised to T RT times MT. T equals 0 to capital T. That is known as MIS. Yeah, I'm really forgetting. These estimators are from Liu et al. 2020. So you will be able to find this paper. Yeah, you will be able to find this paper hopefully on Google Scholar, and they are studying estimators of this type. And these papers are somewhat of a survey paper sort, so you will find a lot of other references as well within this paper, where you will find the history of all of these three different important sampling based estimators. The problem still remains. You may not have mu B, in which case you estimate this product. So you have mu E over mu B that you are multiplying over long periods of time. If each of them is greater than 1, then this product becomes extremely large. And that's why you're only doing estimate for finite horizon. You're not doing estimate for infinite horizon, because in infinite horizon, this product will be either infinity or it will be 0. It can't take any value in between. I mean, it can, but that's very rare. And so the variance of these estimators are extremely high. So ideally you shouldn't be using these estimators, but if you don't have anything else, any other way to estimate it, then these are the only estimators that are available. So they have very high variance. Generally the variance are growing quadratically in T. So the variance of these methods, so variance of V hat is roughly order of T square. Okay, T square or exponential of T? Let me check. It's right. It's actually exponential. So not T square, but it's some lambda raised to capital T. So it's order of lambda raised to capital T, where lambda is something which is greater than 1. There are some very specific cases where you could have a lower variance, and in those cases this MT would not blow up. Okay, so this LT can blow up, this LT can blow up in some cases, but this MT may not blow up in some cases, and so in those cases the variance will not be very high. But none of these three estimators, you cannot say that this estimator is the best estimator, because depending on the Markov chain, depending on the behavioral policy, depending on the policy that you are trying to estimate, one of them would be better than the other. Okay, and so you can refer to this paper, because this paper explicitly constructs 3 different MDPs and shows under what condition which MDP has this as the best estimator, which MDP has this as the best estimator, and which MDP has this as the best estimator. So depending on the situation, one may be better than the other. Any questions so far on this? Yes.
Are these both biased or unbiased?
They are all unbiased. Yeah, so if you take the expectation, remember this is the proof for unbiasedness. Okay, so when you're taking the expectation, you're averaging over the entire trajectory. If you look at this and you average over the entire trajectory of I0, U0, I1, U1, and so on and so forth, this one will have the same expected value. Okay, so these are unbiased estimator, but very high variance. Very good point. So these are all unbiased. Any other question? Okay. So off policy estimation or off policy evaluation for finite horizon, this is the way people have done it in the past. Now, of course, you can come up with a better way or a new way to do the same estimation, but
What is a lambda?
lambda is some parameter. So lambda is some parameter that is a function of p square over k. Okay, so refer to the paper by Peter Glynn to figure out what lambda is. Okay, so it has something to do with the eigenvalue of this matrix p square over k matrix. Okay, so and this p square comes because you are looking at the variance. So when you look at the variance, this term squares, this term squares, this term squares, and this term also squares. But then you are only taking expectation with respect to one of the k. So this k and this k square, one of them cancels. So then you have p square over k.
So is lambda guaranteed to be greater than 1?
Yes, it is guaranteed to be greater than 1. Yeah, yeah. So if you look at p square over k, it is guaranteed to be greater than 1 if p is irreducible, which means that you have a single communicating class. Okay, so a lot of Markov chain theory that goes behind proving these results. So we are not. That's why we are not covering those proofs in the class. Okay. It's going to take quite a bit of time to prove these. Okay. But this particular part, which is that variance is very high, it's a classical result. This result comes from 1991, so everybody knows about it. It's not a new thing. Okay, and the most of the people are trying to figure out how can I. So what are the kind of MDPs where you could have lower variance in these cases? So like this happens in the case of irreducible Markov chain, but maybe you have other kinds of Markov chain where it will not happen. So that's what people were thinking about. Okay, so let's talk about t equals to infinity. As I said, t equals to infinity, you can still do importance sampling. You will get an unbiased estimate with infinite variance. So I guess not a good way to estimate things if your variance is infinity. So what is the idea? The idea is to use fitted Q iteration. So let me write it down. So Q mu E equals to R plus alpha P V mu E. Or should I expand it? Maybe I'll expand it. Let me expand it. Let me write it here. So Q mu E of IU is R of IU plus alpha summation J Piju V mu E J. So that's the Q function, right? So Q learning, we talked about this Q function, and this is the way the Q function is defined for a specific policy mu E. And then you can take the maximization with respect to U, and you get the value function V mu E. So V mu E is I equals to max over U. So we are talking about reward, so this is going to be max of Q mu E IU. Okay. So I have data collected from mu B. I have to evaluate Q mu E. What would you do? Let me erase the board. Okay, so here is the idea. I'm going to write it as RIU plus alpha Q, no, Q is capital, right? So Q let me define, I'll have to define something else. Okay, let me define it as summation U mu E U given I times Q Oh, no. The value function is not max. Sorry. I think I know what the mistake was. Mu E U given I. This is sum over all U. Can you please make the correction here? You have mu E U given I. That gets multiplied to Q and that gives you the value function. So I'm going to substitute all of this here and I'm going to get R plus alpha times summation of mu E U given I Q mu E I comma U. No. There will be J. There will be J. This will be U prime. And then I'll have to do the summation over. I have to do summation expected value over J. Let me do it here. Let me do it in the outer. Let me take the outer expectation. This expectation. Does this make sense? This expectation is given I comma U. Okay, I think now this looks correct. Okay, so this V mu E J, so this expectation I have taken it in the outer expectation. This V mu E J, I replaced it with this particular expression right here. And what I realize is that my Q mu E is supposed to satisfy this fixed point equation. Okay, so Q mu E satisfies expected value of R plus alpha summation mu E U given J, U prime given J, Q J U prime minus Q I U equals to 0. So I have taken this this QIU to the other side and I have replaced this Q mu E with this particular condition, with this function, small q. So the goal is, so now what is the updated goal? I have this data set from the previous policy and I want to compute the fixed point of this particular expression. So how would you do it? You have the data set from the previous policy mu B and you want to compute this Q function. So the way to solve this expression is, I have a function class. This is my function class. I know we haven't talked about function class yet, but for the time being, you can just assume it to be matrices. But very soon we'll start talking about neural networks and whatnot. So in that case, you can think of it in terms of neural network. And you have the following update q hat k plus 1 equals to argmin q in this function class q of expected value of r minus q plus alpha q hat k of j comma perfect. This looks correct. Awesome. This is what it is. Okay. Okay, so you look at the difference, you look at the expression inside this, you square it. So that's the square within the parenthesis, you square it. This is an empirical expectation based on data set. So I put an E hat there depending on how many data points you have. You can compute the empirical estimate of this particular expression. And at every point of time, you compute q hat k plus 1, you substitute it here, and you try to figure out what the solution to this problem looks like. So this is the q here, and the q hat k, which is the output from the previous estimator, is punched in here, and this allows you to come up with an iterative way to compute the q hat, which is an estimate of q mu e based on the data set that you have generated from from mu b, behavioral policy. Okay, so that's one estimator that people have talked about. By the way, I do want to mention about this paper. Where did I get this from? So this is a survey paper. So you will find references to algorithms of this type. This is off policy evaluation in reinforcement learning. This is 2025. It's a recent paper. I got this paper from archive, but it got published this year in some journal. Okay, this paper is by Uehara et al. So that paper will get you a lot of other results on off-policy evaluation. Off-policy, some people call it off-policy estimation, some people call it evaluation, it's the same thing. Okay, so these are all the stuff that people have done in the past maybe a decade or so, or maybe more than a decade, maybe 2 decades. A lot of different algorithms that people have come up with for off-policy evaluation. Any questions so far? Yes. Good question. They've not mentioned whether it converges or not. It's a survey paper, so I'm pretty sure if you go to one of these different references that they mentioned, it would contain some, or maybe the paper might contain some results on the convergence characteristics of this. Typically, these methods would converge under very complicated assumptions. Okay, so take it with a grain of salt. Those assumptions may generally not be satisfied in whatever problem statement you are interested in. Okay. Any other question? Okay. So that's pretty much all that I had for off policy estimation. It's an important field from an applications viewpoint. The papers that have been written so far have made quite a lot of assumptions, which I am very unhappy with, but I can't help it because that makes the math work. So that's what people have studied. I think personally, I think that this is an area where you can try to remove some of those assumptions and see what are the new algorithms. So those algorithms will look completely different from what I've done in the class. But I'm pretty sure you will be able to find some new algorithm in this particular space, both because it's extremely important and it's, in some sense, I think it is also important from a large language models perspective. So there is the current transformer model, which is giving you some output, and you come up with a new transformer model and you want to see whether the new transformer model is going to do better or worse in comparison to the previous one. So I don't know if you have noticed, but the new thing is within OpenAI, you can actually go and buy stuff. Have you checked it in ChatGPT? So I think this feature rolled out like 2-3 days back. And so now OpenAI has become a recommendation company. So you say, okay, I'm cold, I want a jacket, suggest some nice sustainable jackets for me for the winter in Ohio. And then OpenAI will do all the deep thinking and it will say, okay, here is a jacket from Walmart.com, here is a jacket from Amazon.com, here is a jacket from Patagonia.com, and you can go and buy it. You can do the entire checkout within the ChatGPT itself. So the good thing is now they have a recommendation policy. You can go to OpenAI, you can create a new recommendation system, mu e, and then you will have to prove that v mu e is strictly better than v mu b with high confidence. Okay, so off policy estimation would be very useful there. So anyways, exciting times, important theory. I don't like the assumptions, but that's what makes the math work so far. So if any of you are interested, feel free to pick up this topic, and I think go through the papers and the hundreds of references that are there in this paper to get an understanding of what has been done and where you can add value in this particular area and earn lots of money from OpenAI after you do that. And then send me 1% of your net worth. All right. Thank you so much. I'll see you guys next week on Tuesday, and we'll start talking about MDPs over general state spaces. Okay. Thank you.